Hi, I'm Dr. Tasha Ausman,
I'm Dr. Catherine James.
and we're here today to talk to you about a particular wicked problem that we're introducing as part of the graduate course at the University of Ottawa, with that exact title, entitled Wicked Problems. And it's Wicked Problems in STEM, which includes mathematics. And so the 2 weeks that we're here to talk to you about are mathematically driven. And this first week is about voting, which is something that Catherine talks about with her high school students. And I've taught that course, but not for a long time. So Catherine's both a mathematician and also a mathematics expert in this area. And what's interesting about democracy is that it seems like a really fixed term. Like it seems like, oh, we're democratic. This is great.
Yeah, and it seems like we know how to count votes, right? If I
Right.
said, let's have an election and which option wins, it seems like the answer should be obvious. And that's not at all the case.
Right. So is winning really winning? And especially at this time, like politically speaking, where there's so many elections going on or they're about to go on, and that there's a lot of geopolitical things at stake, it's really interesting to think about how students in the K to 12 system, but even beyond, think about democracy and the concept of voting as intrinsically good from a value standpoint, or is it like fair? I cast my vote, it has a lot of meaning. Or if you don't vote, you're not doing the right thing, or you don't have the right to complain in a democracy if you don't cast a vote. But like, how is that a problem in terms of STEM? And how is that like a wicked problem that we should address maybe through some mathematics and like, along the way?
Yeah, for sure. And so, what I'd like to do first is take you through some of the main different voting methods. We'll kind of look at an example, we'll look at some of the math behind it, and then we'll move into some of the problems.
But before Kate gets into the math, I'm actually going to pause for a second and just bring up this diagram, which I'm sure Giuliano has brought up in the course because he's framed the course as a series of wicked problems. And I'm sure you've gone through Riddle and Weber's conceptualization of what constitutes a wicked problem. And so the 10 properties of wickedness, at least in planning theory, especially planning and social policy, from which these criteria emerge, have a bunch of different elements that apply to what we're going to talk about. Because what we're talking about is mathematics and democracy. And it's actually about democracy, but it implicates mathematics, which makes it a STEM problem. And some of the things that are in the 10 criteria directly apply to what Kate's going to talk about in articulating the actual criteria, which is going to take about like 25 minutes of the different voting methods. And I really encourage you to follow along and actually follow the math. Like if you're a scientist and you're in this course, you're in it to win it, to learn this. And I also would say that like if like applied 11th grade math students can follow this, the mathematics of various democratic voting methods and ask really important social questions about them after the fact, we can do the same thing. But before that, I do want to like articulate that some of these things really, really apply. I think almost all of them actually apply to this problem, and that the idea that there's no clear definition, like there's no clear definition of what it means to vote, and for your vote to count. And we're going to see that how that pans out mathematically, but we're also going to see how that pans out socially. And one of the readings for this week is also about the geometry of gerrymandering, which looks at how there's intense algorithms used, but also the notion of where you are, who you are, and how you're counted impacts your impact on the voting system in countries like the United States. There's also the no stopping rule, which you might have talked about in relation to other wicked problems in the course. Climate change is a really good example of one that kind of has this no stopping rule applied, which is that there's not an inherent logic as to when the problem is solved. So one of the issues too is that, are we solving the problem of democracy? Well, democracy is not inherently a problem, mathematically or otherwise. It's actually the attempt to have um, a solution to all of us coexisting in a particular society, whether that's Canadian or elsewhere. And most importantly, here, as we can see, that solutions are not right or wrong, but better or worse. And then we'll talk a little bit about fairness at the end of the math bit and kind of loop back on this criteria here. I know one critique I have of Riddle and Weber is that they said, unlike mathematics and chess, which have finite solutions, problems of social policy don't have these, like, intrinsic closed end structures of internal logic, which is interesting because mathematics is not close-ended and doesn't always have internal logic as well. So that's going to be part of the unpacking some of the things, like having no final end to the solutions. I think these are unique problems to democracy, and maybe looking at all of these 10 criteria might be part of your reflection for this week, and to say, well, how do voting methods as a construct within STEM, once you go through the math for the next 20 some minutes with us on video, how are these things that you can reflect on, and like how do the voting methods themselves, or even just the concept of the counting, and then if you take a look at the fairness criteria, which we'll explicate in a document that we're going to attach in the module at the end, how do those things help us ask questions about what kind of wicked problem this is, and why looking at voting criteria matters, and whether there's a kind of functional literacy in society around it. So just some food for thought. And now switching over to Dr. James to tell you all about how to count votes. Great. So we were just introducing the concept of a wicked problem as one that can be where STEM and society intersects. And I think this is an important one because we all cast votes and we think that those votes count. And we also think perhaps of democracy as a kind of monolithic thing. You cast your vote and it means something. And maybe that one of the subtle questions is, like, what does your vote mean? And does it mean the same thing everywhere? And Kate's going to come along here and really explicate her expertise, which is looking at how votes are counted in different democracies around the world, to show us that maybe there are some different ways that the votes are counted, and that maybe questions around fairness and around vote counting and around the concept of who wins might be in contention for all of us.
Fantastic, thanks. So what we have on the screen is the results of a hypothetical election. Okay, so what we have here is we have 1,255 people. And these first 1,255 people, we're looking at these 4 different candidates, candidate A, candidate B, C, and D. And what these people did was they ranked their candidates in preference order. So candidate A was their first choice, candidate B was their second choice, candidate C was their third choice, and candidate D was their fourth choice. These next 1,270 people also ranked all 4 candidates, but they ranked them in a different order. C was their first choice, and then B, A, and then finally D. These 1,280 people also ranked all 4 candidates. Their preferred order was D first, and then A, B, and C. And then finally, these 1,260 folks ranked the candidates. B was their first choice, and then C was their second choice, D was the third choice, and A was the fourth choice. Now, if you're in Canada, the way that we look at votes isn't to look at what we call a ranked ballot, but it really is just to look at your first choice, right? When you go in and you cast a vote in an election, you cast your vote for your most preferred candidate. And so when we talk about some of the methods, we're only going to be looking at this first place row, and then sometimes we're going to be looking at all of them. Okay, so one common method for determining who wins an election is something called plurality. And under plurality, what we do is we only look at these first choices, the number of people who ranked the candidate as their first choice, like we do in Canada. And the candidate that gets the most number of votes is the winner. So under plurality with this election, candidate A would receive these 1,255 votes because those 1,255 people ranked candidate A as their first choice. Candidate B would get these 1,260 votes. Candidate C would get these 1,270 votes. And then finally, candidate D would get these 1,280 votes. The winner would be the candidate with the most number of votes, and that in this case would be candidate D. So let's just make a note of that up here. D wins. Okay. Now, what's interesting about these this election is that the results are very close together, right? The candidate with the fewest number of votes, candidate A, has 1,255, and the candidate with the winning candidate has only 1,280. Right? So the spread between all four of these candidates is very small. So we might not always be comfortable with saying candidate D wins an election when the majority of people would like somebody who's not candidate D. So one way that we can strengthen this idea of plurality is by using an election system called majority. Now, in majority, what we do is we look at, again, just the first choice votes. And in fact, the results are identical to plurality, right? So A would get 1,255, B would get 1,260, C would get 1,270, and D would get 1,280, right? So plurality, right? Remember, it's the most votes that wins. For majority, we need more than half to win. A candidate would need more than half to win an election. So more than half. So let's take a look at the total number of votes here in this election. So the total voters would be 1,255 plus 1,270 plus 1,280 plus 1,260. And so the total number of voters would be 5,065. If we want more than half, well, let's figure out what half of that is, right? So 5,065 divided by 2 gives us 2,532.5. So an option, a candidate would need more than 2,532 votes in order to win. And what we see is that none of these candidates has more than 2,532 options. So under majority, there is no winner. Okay. This is a problem with majority. It would be really frustrating to hold an election and, to have all the expenses of the election, everybody's spending their time going out to vote, only to be told when the votes are tallied that there's no winner. So majority is more satisfying when there is a majority winner. However, a lot of times there's not. So what do democracies in other parts of the world do, right? If majority isn't particularly feasible and plurality isn't particularly appealing, even though it's a method that many countries use, what are some of the other options? Well, we're going to look at 3 other options. Okay? One of those options is called elimination. And I want to look at elimination next because it starts just like plurality does and just like majority does. Sometimes this is called majority with elimination, right? It has a couple other names that it goes by as well, but typically we can think about this as majority with elimination. So what elimination does is it says, you know what? We still want an option to have more than half of the votes in order to win. But we recognize that we need a winner from the election. So let's start with the very same results that we had. So A had 1,255, B had 1,260, C had 1,270, and D had 1,280. Now, we know that none of these options has over half of the total votes, because what we determined above was that we need more than 2,532 votes in order to win. So none of these options has a majority. And I'm just going to erase some of these marks that I've made so I can draw on this table a little bit more, and hopefully you can kind of follow what's going to happen here. So what happens with elimination is that we're going to take the option with the fewest votes. Okay, so the option with the fewest votes is option A, right? It has 1,255 votes, which is the fewest. So we're going to get rid of candidate A. We're going to pretend like candidate A was never in the election to begin with. So up on this screen, I'm going to cross off everywhere that candidate A was. And it's not going to shift the votes much, except for these 1,255 people, right? Their preferred option is no longer available, right? If candidate A never was part of the election, then these 1,255 people would have put candidate B as their first choice, right? Because it was their second choice. If their first choice is gone, let's redistribute these 1,255 votes to candidate B. So what happens is candidate B gets 1,255, and 1,260 plus 1,255 gives us 2,510. Okay, sorry, 2,515. Let's fix that. Now, that's fantastic, but 2,515 is still not over half. So candidate B is close to winning, but candidate B hasn't won yet. So we need to eliminate the next lowest option, right? So now candidate B has 2,515 votes. Candidate C has 1,270, and candidate D has 1,280. So the next lowest option to get rid of would be candidate C. Okay. So let's get rid of candidate C in our table above. And again, for these 1,260 people who liked B best, well, they still like B best. And so those 1,260 votes still go to B. For these 1,280 people who liked D best, they still like D best. So those votes don't change. But for these 1,270 people who used to like C best, if C was never an option, those votes are now going to B. They're going to the candidate next down on their list. So B gets some more votes. So B is going to get those 1,270. And if we add 1,270 to this, what we get is 3,785. And so now B is going to be the winner. We work down, we keep eliminating the lowest choices until we come up with a winner. So it solves the problem of majority, where we often don't have a winner. And it still takes everybody's vote into consideration. And it forces us into a position where we're choosing a candidate that people prefer. Hopefully what you see here is that so far, all three of these voting methods have given us very different results. Plurality has given us D as the winner, majority has given us no winner, and elimination has said that B should be the winner. Okay, so another voting method that's used throughout the world is something called board account. Okay, and board account is named after a person who popularized this method. Wasn't necessarily the first to use it, but did help popularize this. And what happens with board account is that we pay attention to the first choice, the second choice, the third choice, and the fourth choice, just like we did in elimination, right? Where we, if the first choice wasn't available, we went down to the second choice. But with board account, we pay attention to these rankings all at once. We put all of that information in at once. And basically what we do is we assign points. So in the case of 4 candidates, the fourth place would receive 0 points. the third place candidate would receive 1 point. The second place candidate would receive 2 points, and the first place candidate would receive 3 points. Okay. So because they receive 0 points, we don't actually have to pay attention to this bottom row at all, which is kind of nice. So let's look at what that looks like. So for candidate A, right, candidate A gets these 1,255 people all voted for candidate A for the first choice, which means the candidate A gets 3 points for each of these 1,255 people. So candidate A gets 1,255 times 3, plus, let's look at these 1,270, kind of this next group of people. These 1,270 people ranked candidate A as their third choice, which means candidate A gets 1 point for each of these 1,270 people. So we'll add 1,270 on to candidate A's total. These 1,280 people put candidate A as their second choice. So candidate A gets 2 points for each of these 1,280 people. So it'll be 1,280 times 2, right? And we'll add that to the total. And then finally, these 1,260 people put A as their last choice. And so candidate A gets no votes for those folks. And so if we look at that total, we have 1,255 times 3 plus 1,270 plus 1,280 times 2, which means candidate A has 7,595 points. Okay, and let's see what candidate B ends up with. Candidate B would have 1,255 times 2, because these 1,255 people put them second. So it's 1,255 times 2, plus 1,270 also times 2, plus 1,280, and these 1,280 people put B third. So candidate B just gets 1 point for each of those. And then finally, for these 1,260 folks, candidate B was their first choice, so they get 3 points for each of those. So that's for candidate A. Here's candidate B. If we do 1,255 times 2, plus 1,270 times 2, plus 1,280, plus 1,260 times 3, we end up with 8,842 points. Okay. So B is beating A, but let's see about candidates C and D. Candidate C would get 1,255 times 1, or just 1,255. Candidate C would get 1,270 times 3. Candidate C would get 1,280 times 0. They get no points for that, so we don't have to pay attention. And then 1,260 times 2. So let's see what candidate C's total is. 1,255 plus 1,270 times 3 plus 1,260 times 2 would give us 7,585. And then let's look at candidate D as well. Okay, and then finally for candidate D was the last choice for these 1,255 people. So candidate D gets none of their votes. D was also the last choice for these 1,270 folks. So D gets no points for them. But for these 1,280 people, D was their first choice. So we get 1,280 times 3. And then for these 1,260 people, candidate D was their third choice. And so D gets 1 point for each of those 1,260. So we have 1,280 times 3 plus 1,260. And what we end up with is D has 5,100 points. And for board account, what we do is, now that we have the points, we look at the option that has the most points, which in this case is B. And so B would be declared the winner. Border count doesn't always give us the same winner as majority with elimination. Sometimes it does. And in this case, it did. Now, we have one last voting method to consider. Okay? And the last voting method we need to think about is called Condorcet, or sometimes it's just called pairwise comparison. Again, Condorcet is named after the person who kind of made this method famous. Again, not the inventor, but a guy who made this famous. But it's often also called pairwise comparison. So we have the Condorcet method. And what the Condorcet method does is it's slightly different than these other voting methods. And what it does is it says, let's imagine a scenario where there were only two candidates. So for example, candidates A and B, who would win the election. And then let's imagine a scenario where there were only two candidates, but those candidates were A and C, right? And then let's imagine a scenario where there were two candidates, but they were only A and D. And then we would compare only B and C. We would compare B and D, and then we would compare C and D. So what we're doing is we're putting every candidate in a pair, right, with every other candidate and seeing who would win the election if those were the only two candidates available. So let's take a look at what that ends up being. So if we're considering an election only between candidates A and B, then let's look at how people would vote. These 1,255 people like A better than B. So A would get those 1,255 votes. These 1,270 people, they like B better than A though. If C were never an option, right? These 1,270 people would choose B first, right? So we're looking at their rank, and is A ranked above B or is B ranked above A? So if we're only considering A and B, A gets these 1,255 votes, B gets these 1,270 votes, A gets these 1,280 votes because these 1,280 people like A better than B, and B gets these 1,260 votes. And if we do some quick math, if we have 1,255 plus 1,280, that gives us 2,535. And if we look at B, which is 1,270 plus 1,260, we end up with 2,530. So it was a close contest, 2,535 to 2,530, but A won. So I'm just going to circle A here to make a note that A won. Now, if we look at A and C, so we consider only A and C, right? We pretend that A and D don't exist at all. Then these 1,255 people, they like A better than C. So A gets 1,255. These 1,270 people like C better than A. So C gets 1,270. These 1,280 people like A better than C. So A gets 1,280 more votes. And these 1,260 people like C better than A. And so C gets 1,260. And so the results in this case are exactly the same as A and B. A has 2,535 and C has 2,530. So A wins again. So if it were only a contest between A and B, A would win. If it were only a contest between A and C, A would also win. Let's look and see what happens in a contest between A and D. In a contest between A and D, these 1,255 people like A better than D. So A gets those 1,255. These 1,270 people like A better than D. So A gets 1,270 more. These 1,280 people like D better though. So 1,280. And these 1,260 people also like D better than A. So if we have 1255 and 1270, that's 2525. And D has 1280 plus 1260, which is 2540. So here, D would beat A if we were only looking at this comparison between A and D. Okay. Let's keep going, and then we'll talk about some of the problems posed by Condorcet. So we did A compared to B, A compared to C, A compared to D. Now let's look at B. Well, we already did B and A as a comparison. So we need to look at B and C as a comparison. So if we look at B and C, 1255 goes to B, 1270 goes to C, 1280 goes to B, and 1260 goes to B as well. And so even without counting those up, we can see that B's total is going to be bigger than C's. Let's look at B and D. 1255 goes to B. 1270 goes to B. 1280 goes to D. And 1260 goes to C. Again, sorry, 1260 goes to B. So again, we can see that B would beat D. Now finally, let's look at the last comparison, right? We did A compared with everything, and now we've done B and A, B and C, B and D. We've done C and A already. We've done C and B already. So the last comparison we need to do is C and D. So let's take a look. These 1,255 people like C better. These 1,270 people also like C better. These 1,280 people like D better. And these 1,260 people like C better. And so we end up with C beating D. So how do we possibly figure out who wins using Condorcet? Under this method, an option or a candidate would have to win every single pair that it was involved in. So in every pairwise comparison, it would have to be better than the alternative. So we see A almost wins. A beat B, A beat C. If A beat D here, then A would have won, but it didn't. More people want D than want A, so it doesn't make sense for A to be the winner. So let's look at D. Does it make sense for D to be the winner? Well, D beats A, but B beats D. So it doesn't make sense for A to win because more people would prefer D. It doesn't make sense for D to win because more people would prefer B. It doesn't make sense for B to win because more people would prefer A. And it doesn't make sense for C to win because more people would prefer A. So in this case, there's no winner. It's one of the problems with Condorcet. So we've just been through a bunch of different voting methods. And so I think the question really is, so what, right? And what you saw is that sometimes there are voting methods that don't lead to a winner. That's a problem in a democracy. But also that there are voting methods that lead to different winners. And so depending on the voting method that we choose, we may have different winners. If the exact same election happened in different areas of the world, we might have different winners, even though we're all functioning under a democracy where each person gets one vote. How we tally those votes makes a big difference. More to the point, though, and I think the bigger problem for this course is not just that different voting methods can result in different winners, but also that each of these voting methods is fundamentally flawed in some way. So if we look at kind of the intersection of politics and mathematics, one of the areas of a lot of research was kind of around these voting methods and what makes a fair voting method, right? How do we choose one voting method over another? And there were some fairness criteria that were developed. There were 4 of them. And those are all kind of put in a document that's on Brightspace that you can read them. So for example, the independence of irrelevant alternatives. So if an option that didn't win were removed, it shouldn't change which option wins. If an option wins under Condorcet, which was that last method we did, which was fairly strict, very difficult to get a winner. So if an option wins under Condorcet, it should win under any other voting method. And there's some mathematical reasons why we would want that to be true. And what we find is that each of the voting methods, except for majority, violates at least one of those fairness criteria. So there is no actual fair voting method. Majority is slightly different because it's a threshold that's almost impossible to achieve, especially when we have more than 2 candidates. So it's not a practical voting method.
And that leads to a lot of questions around whether winning matters and whether winning and fairness are the same thing and how those 2 things intersect. So that could be something also to think about that you're looking at in this module when you're looking at some of the criteria for both voting as a potentially wicked problem in our society, a mathematical problem, but also a social one. And all of that entwined with what we think it means when our vote counts for something and who's being counted and what counts. And also the kinds of people who are still and continue to evaluate both the history and also the futurity of different kinds of voting methods along the way. So when we talk about voter reform, we're also talking about a whole complexity of algorithms, potential technological innovations that go into like perhaps looking at new mathematics for potential voting methods that we haven't thought about. Like, is AI going to contribute to those in the future? I mean, these are all questions we don't really have answers for yet.
Yeah, and one other thing that I wanted to bring up is a fairly popular voting method used throughout the world that doesn't quite fit within what we've been talking about, which is proportional representation. And so we aren't talking about it in this case because proportional representation doesn't give us a single winner of an outcome of an election. It's how we divide up the seats. And so it doesn't quite fit into what we're talking about, but it is a very popular voting method that's used fairly widely, has its own set of problems as well, but not quite consistent with what we've been talking about here.
Right. And proportional representation, I think, was on the table in Canada as well.
Mm-hmm.
So like, if 80% of the voters, vote for a particular party, they get 80% of the seats. And it's not by writing and it's not first past the post. And that could be a really interesting way to say every single party that runs has a potential seat in Parliament, in our case, and opens the door for a lot of other social, because if I want to run the, Purple People Eaters Party, and I get enough votes, then proportional representation might give me a seat in the House of Commons, and that could be a really great thing.
It's really appealing in a lot of ways because it opens the door for some smaller parties to have a voice.
Yeah.
So, for example, the Green Party in the recent Canadian elections would have ended up with a lot more seats in Parliament than they do now. And some other parties would have ended up with seats where they don't currently have seats. It's a double-edged sword, though, because who gets to dictate which parties get the seats, right? If we're opening it up to minority parties and we're especially, we are left leaning it all in the ideals of the Green Party really appeal to us, then having parties like that have seats in our government might be really appealing. But if we open the door to, some smaller groups, we're opening the door to all smaller groups. And so we don't get to say yes to the Green Party, but no to...
Well, we have the Communist Party of Canada, which always gets like a very small minority vote in several ridings, or actually many ridings across Canada, and sort of the Communist Party of Canada would get some votes.
And maybe we're okay with that.
Yeah,
but we might not be okay with hate groups also getting seats in our government if they got enough votes.
Yeah. Also an interesting read just on the way out. If you're interested in the history of Mathematics and Democracy. This book called Numbers Rule, which is by George Spiro, is a fascinating read, and it goes through a lot of the things that Kate was talking about specifically mathematically, but also like some of the histories of voting and how some of the counting came to be, particularly in the West, like Western Europe. And so it's sort of from Plato to the present. So if you're looking at this through a Western epistemological tradition. So we hope that you really enjoyed this introduction to one of the wicked problems of this course.
Thanks so much.
Have a great day.